I'm going to own it. Biosynthesize, the way that our body makes some of the specialty lipids. And we've already talked about mixed function oxidases. And remember, that was an enzyme that simultaneously oxidizes two different components or two different substrates in that same cycle. Okay? But we're also going to learn a little bit of the vocabulary so we can start to add some of these into our handy dandy, I don't want to say organic chemistry tool belt, but names of enzyme classes. So oxidases really do redox reactions as well, okay, just like what we've seen before. Remember, if it uses NADH and FADH2, many times they're called dehydrogenases. They can also be called oxidoreductases. That's the official name under the, I'm drawing a blank, Enzyme Commission, I think. The classification, they like the term oxidoreductase, so it does both oxidation and reduction reactions. But historically, there are a few, like Cytochrome C oxidase and Cytochrome C reductase that we saw last chapter, where they've kept their historical name of oxidase or reductase. So oxidases in general just means that they're going to do some type of oxidation reaction, and it utilizes oxygen, O2, like cytochrome C oxidase, but the oxygen's not in the final product. And I know that that's kind of, it's going to be easier to see what I mean by that whenever we look at examples. And so my pen did die. That's not good. I apologize because I'm going to have to, there are some exceptions, just like the English language, there are some exceptions also here. I can't believe it's dead. And unfortunately, the iPad only has one port. Why can't they, you know what? Spirit of Steve Jobs or whoever it is that oversees and compels Apple to do what they do. Put in more than one port. I think I can do it here, but it's going to take a while. All right. So cyclochrome C oxidase. The cytochrome was oxidized, but no oxygen was actually added. An oxygen element atom was added to the cytochrome C. You know, it just meant that it lost electrons. Then we have another group of enzymes called oxygenases. Okay, so we've just like we had synthase and synthetase, which what was the difference? What is a synthetase? It uses ATP or GTP in order to synthesize to make something, whereas synthases typically don't. Well, oxygenases don't use ATP, but we differentiate between an oxidase and an oxygenase because oxygenases do oxidation reactions. It's like a tongue twister, but the elemental oxygen is included into one of the products. Okay, and so we'll show an example of that. So many times what we're talking about here is you'll see it where it now all of a sudden becomes an alcohol. Something that was an alkane becomes an alcohol because that oxygen got added and the oxygen came from O2. Or maybe it's become a carboxyl group, whether it's a ketone, aldehyde, a carboxylic acid, something like that. I guess in theory, ester. Is the idea. And oxygen all of a sudden appears, I shouldn't say all of a sudden, the oxygen appears in the product. And so it's called an oxygenase. Okay. So Cytochrome P450 are technically oxygenases, even though it wasn't in its name. That's the classification for it because it takes an alkyl group, as I just mentioned, and converts it into an alcohol. But then they take these oxygenases and they divide them into even subcategories further, okay, which are clinically important in medicine, right? So we have oxygenases. That literally means that an O2 gets split and one of those oxygens, at least one of those oxygens, are going to be added to the final product in that form of oxidation. So they split them up into what's called a monooxygenase and a dioxygenase. And it's just like the name implies. Monooxygenases means that only one of the one of the oxygens from O2 ends up in the product. A dioxygenase means that both oxygens of O2 ends up into the product. Okay. So otherwise, like naming and things like that is very similar to what we've seen before. It's just, this is, if we had time, you know, a lot of times I'd even review not all, but try to review as many of the classes of enzymes that we've gone over, like transferases and synthases, synthetases, kinases and phosphatases and phosphorylases, and nucleases, proteases, and lipases, and tigers and bears, oh my, kind of thing, you know. But now we have, under that helm of redox reactions, we have the dehydrogenases. Then we have oxidoreductases, reductases, oxidases, and now oxygenases. And the oxygenases can be split into mono and di. Okay, so this is an example. This is tryptophan 2,3-dioxygenase. It should be fairly simple. You know, we have tryptophan, hopefully you recognize, which is amino acid. And now, if you notice, the O2, one oxygen atom gets added into the alkane, becomes a ketone, and then we also have added onto the nitrogen group an aldehyde. And the old-fashioned, I shouldn't say old-fashioned, an old term for an aldehyde group, it's called the formyl, so that's what that formyl means. Like formaldehyde means it's only has, I should say, it means it's a one carbon containing group. Just like acet, ACET meant two, well, formyl means one. So this is like N-formyl kynurenine, which is actually really important. I think we're going to try to get, hopefully we'll have time to go through some of the neurotransmitters and things like that. And so this is important for tryptophan's metabolism. Okay, but this is a dioxygenase. Okay, Cytochrome P450, we mentioned before. Technically, it's actually a protein family, and there are hundreds of them. So it kind of gets, it's like a generic name almost that gets used. So like calling, you know, all sodas Cokes or something like that. And what they do is ultimately they're going to take an alkane and transform it in vivo, obviously, to an alcohol. So for those who had organic chemistry, if you remember, it was not easy to do that in vitro. You had to usually activate the alkane with free radical halogenation or something like that. Then you had to do a substitution reaction, to say the least, and so there are multiple steps. We do something similar here, except obviously we don't have those conditions inside our body. And so what we're doing is this is just using Cyclochrome P450, and it comes from NADPH, which then reduces Cytochrome P450 reductase, which is an iron sulfur protein, which is what we've seen before, which then it's what reduces Cytochrome P450. And Cytochrome P450 then takes that alcohol takes that alkane, transforms it into an alcohol at the expense of an oxygen atom from O2. And so that's why this is a monooxygenase. Okay. Then we have our icosanoids. We've actually discussed this briefly. I usually cover it in passing when we discuss lipids last semester. But these are signaling molecules that act in short range, so they're usually part of like the paracrine system, similar to that if you think back to AMP. So typically they get released, whenever they get released, they only affect the local cells, if not the original host cell. And it also just makes sense once you see what they look like. I mean, they're very hydrophobic, so you wouldn't want them to release them for long term or long distances, since they're hydrophobic. Okay. So here we go. Here we have the icosanoids. So if we look here at its metabolic pathway, is we have remember, they come from arachidonic acid, arachidonate, and we have a phospholipase, and it's going to cleave it. Okay, the original phospholipid. So now we have arachidonate, and once again, I don't ask you to memorize their common names. I would expect you to recognize this kind of nomenclature that they have here. Then what happens is we have these COX enzymes, which are Cyclooxygenase enzymes. And so if we notice here, we take arachidonate, we add in the O2. So is this cyclooxygenase? Are these going to be monooxygenases or are these dioxygenases? Because we have, technically, there's 4, because we have an O2 here and we have an O2 there, so these are dioxygenases. Then there's a peroxidase activity that transforms that carboxylic acid into an alcohol here. And then this goes on, this is PGH2. PGH2 then goes on to make either prostaglandins or thromboxanes, which we've talked, has a whole host of things like vasodilation, inflammation, things like that. Cyclooxygenase are the COX enzymes. Technically, there are 2 isozymes in mammals. There's one that's called COX-1 and COX-2. COX-1 is important for prostaglandins. That has to do with your stomach, that one in particular. And then COX-2 are prostaglandins that look at inflammation, pain, and fever. So what happens here is that they're also called prostaglandin H2 synthase, but everyone just calls them the COX enzymes, COX-1 and COX-2. A lot of your pain relievers like aspirin and ibuprofen, what they do is they inhibit the COX enzyme. And so, therefore, if you don't ever make the prostaglandin thromboxane, then the idea is it will bring down inflammation or swelling. And one of the reasons why, one possible reason that you have a headache is due to inflammation in a very confined spot, since your brain, in the blood vessels there and everything is very confined. They don't have room to move or to expand. And so by decreasing this, then the levels of this, therefore inflammation should go down. But, whoops, before I go out of the way. Oh, whoops, I'm jumping the gun there. Jump the gun. So this is just one of the ways, let me make it smaller, that they work. Okay. Now we have ibuprofen and naproxen, which are called NSAIDs, which stand for non-steroidal anti-inflammatory drugs. They usually look like the substrate or some type of intermediate. This is just one example. This is aspirin, acetylsalicylate. And if you notice, this is called a suicide. This one's a suicide because it's irreversible. So what happens is you've got your enzyme, the aspirin gets added onto that enzyme. Whoops, I went the wrong direction. And now it's irreversibly acetylated. So the enzyme is dead. So it's a suicide inhibitor. If you think back to last semester when we talked a little bit, which we don't see that a lot. Most of the time when we did inhibition, we did those that were reversible, but this is an irreversible one. Okay. All right. So what are some of the problems with these? If you just think about it, what's the problem with the COX inhibitor? If it's not very specific, what could be the side effects? Because if you think about it, if it's too promiscuous with the COX enzyme, it may not take care of it may take care of the one that is the inflammation for the headache, but at the same time affects the prostaglandin that's for the gastric mucin that you need, right, for your stomach. And so that's why those are the kind of things that happen, okay? So the COX-2 inhibitors, many times, to some extent, also affect COX-1, okay? And that can have different side effects. So this is one of the reasons why sometimes you hear about aspirin or some of the pain relievers that can also cause stomach issues. And that's relatively, or naproxen is a really good example. It's one of the reasons why you should take naproxen, like Aleve. You should take it with food if at all possible. But there are even greater defects, okay? So what happens is They looked at, they see the crystal structure of the COX enzymes. They found some that they said that were specific only for COX-2. So therefore, COX-1 would be great. You wouldn't have any problems, okay? And so they thought these were miracle drugs, especially in the late 1990s and early 2000s. Some examples, okay? So like Vioxx, Celebrex, and some of these. So they started to sell these out the wazoo. That's the scientific term, by the way, at the wazoo. But what happened is that they've since actually had to take them off the market. There's been class action lawsuits because in reality, there just wasn't enough. Even though the whole process of getting drugs approved can take a long time, this is one instance where it shows that sometimes that's good because they did do enough background research on it and come to find out some of these actually had unintended side effects that were fatal, that caused heart attacks, some other issues that seem to be unrelated by the fact than what they thought. So it's one of the reasons why it does take, this fine balance that you have to walk between trying to quickly get drugs approved and out into the market, and yet at the same time looking out for long-term side effects. Okay. And another thing bioethically that you want to think about though is what about someone who's dying from a disease that's incurable and lethal, so therefore maybe he or she would be willing to take the risk of some of the side effects in order to either find a cure or find an alleviation of pain or what have you. And so it's never nearly as cut and dried as what some people make it out to be. Are there any questions? Because that was the end of part 2, and then I'll start it because we're a little off in the ways that I normally do it day-wise. So the big thing here is we learned about oxygenases, and sometimes you hear about these COX inhibitors or COX drugs, and now you know where they come into play. Oh, yeah. Mm-hmm.
So COX inhibitors, they block the formation of the glycosides?
Oh, so here, I'll show you. Let me go back.
Like, what is the relationship?
So the question was, like, how do these COX-2 inhibitors work? And so what happens here is that these COX enzymes at this point, they do a couple of different things. They're only showing in this instance one particular one, but in reality there are small differences here of the COX enzymes. So COX-1, what it would do is it would go on to make the prostaglandins that's important for your stomach, for instance, whereas COX-2 isoform goes on to make the prostaglandins that are important for inflammation, pain, and fever. And so the idea was if you could take a COX-2 inhibitor, you could inhibit the COX-2 and take care of your fever or your headaches and things like that and leave the stomach alone. Unfortunately, they aren't specific enough. Things like aspirin and some of these Aleve, to where they do also affect COX-1 to a lower extent. And so that's when you can have some stomach problems. Then the way some of these other, it's called rational-based drug design. I wouldn't ask you guys to know that, but it's where scientists then did crystal structures and they found out what the enzyme for COX-2 looked like, and they found out how the substrate binds, and so they thought, well, let's make something that looks as much like that substrate as possible, because then our goal is it will only affect COX-2. And so they made Vioxx and Bextra and Celebrex. Unfortunately, it had other side effects that they didn't even expect at all that had to do with your heart and issues with that, your regular heartbeat, I think, technically. But, and so that's why, ideally, it would be nice to have the COX-2, one that was specific for COX-2, because then it would inhibit the formation of the prostaglandins, that coursinoids that cause inflammation, so swelling, pain, and fever. Our body does need this. That's one way that we fight and combat things, right? The fever is combating, infection and so on. But it's only whenever it goes out of whack that we want to make sure that we take care of it. Does that answer your question? All right, thanks.